Okay, testing. Looks pretty good. Hope you guys can hear me. Let's start out. Good day. It is Tuesday, December, 8th, I guess, because it's the 8th day of Advent of Code. And we are here solving these problems sight unseen at first, live, and generally in Go, sometimes in Python, depends on how it works, but we're going to jump right in. I've already got things set up today, so I'm going to share my screen and show you what I have. So the windows I have here are the Advent of Code window in the upper left, the command line in the lower left, and Visual Studio Code in the right. I have already created a template project that just loads the input files for me. That's pretty much true of every Advent of Code problem. We try to do that. What I'm hoping I'm doing here is showing you guys a little bit of computer science, hopefully. The way that somebody who's been at this a while thinks. So hope you enjoy. Let's get into it. Start by taking a look at what day it has to offer. All right. As I always say, our fiction is kind of, we're taking a trip, and this time we're now on looks like our second airline flight. And let's just talk about the problem. Your flight to the major airline hub reaches cruising altitude. You're interrupted by the kid sitting next to you. Their handheld game console won't turn on. They ask if you can take a look. You narrow the problem down to a strange infinite loop in the boot code, which is our puzzle input. So this is where it gets fun. They've done this in the past, where actually they end up reusing a virtual machine that they build over the course of several puzzles. And so it's likely that the code we write today is going to be reused, if not tomorrow, in other episodes of this thing. I love this idea. I enjoy virtual machines. I enjoy computing devices. I enjoy sort of assembly language programming. Not that I do it for a living anymore, but I used to. Building a VM is fun. It's fun to make it, try to make it performant, try to make it interesting, whatever. We don't have to make it typically too performant in a thing like this, but let's see what we got. The boot code is represented as a text file with one instruction per line. Okay, that sounds like it's assembly. Each instruction consists of an operation, ACK, which is accumulator or something, accumulator, jump or no op, or nop, and an argument, a signed number like +4 or -20. So it's opcode, operand on each line. ACK increases or decreases a single global value called the accumulator. ACK +7 would increase the accumulator by 7. Okay, the accumulator starts at 0. Okay, so there is an accumulator. A virtual machine has a register. That register is called an accumulator. Usually in, at least old style 8-bit CPUs that I grew up on, there was always main register, which was the accumulator, typically called A, and like Z80 opcodes or whatever. And then there were various things that would operate on the accumulator. Jump jumps to a new instruction relative to itself. So a jump is a relative jump. So you're saying jump, +5 means jump forward, jump -5 means jump backward. Jump 1 continues to the instruction immediately below. So jump 0 would be an infinite loop right in that one instruction. Jump 0 means jump right to myself. So in many many assembly languages, JMP is not a relative jump. It's an absolute jump, but in this case it's relative, so that's fine. No op stands for no operation. It does nothing. And the instruction immediately below it is executed next. Okay. For example, considering the following program, and it shows us a little program which is nop0, ac1, +1. Now this is interesting. They have pluses and minuses before every operator. So that's a little bit unusual. It may mean that in the future they're going to take the plus or minus off and do absolutes as opposed to relative, but we'll worry about that later. So this is our sample code. So even while I'm here, I'm just going to take this and copy it into our sample input because that's a useful thing to do. So here's input sample.txt, and this is our sample program. Okay, these instructions are visited in this order. No op 0, ac +1, so adds 1 to the accumulator, jump +4. Now that jumps 1, 2, 3, 4 to here. Ac +1 adds another value to the accumulator, so now accumulator is 2. It goes here. Jump -4, so 1, 2, 3, 4. Ac +3, so that now makes the accumulator 5. Jump -3. 1, 2, 3, back to the ac +1, and now it's going to, the value is going to be, well, we're re-executing that instruction. All right, so they say, so they're explaining how it worked, and I just kind of walked through that a little bit. This is an infinite loop. With this sequence of jumps, the program will run forever. The moment the program tries to run any instruction a second time, you know it will never terminate. That's not generally true in programming, but in a programming language without conditionals, which is what we have right now, that's a valid statement. So immediately before the program would run in an instruction a second time, the value in the accumulator is 5, which is what we had just walked through. Run your copy of the boot code immediately before any instruction is executed a second time. What value is in the accumulator? So there's our question is to detect an infinite loop. Because I suspect that we're going to keep reusing this VM, I'm going to build the VM. There's other ways of doing this problem. You could make this a simpler problem by essentially it's the same problem as detecting an infinite loop in a linked list or something like that. But because I suspect we're going to use this as a VM, we're going to actually make it as part of the VM. And now the question is, how do you track the operation? There's one way that we could track this list of repeated instructions, and that would be like storing them in a map or a list and checking to see every time we go to run an instruction if that element is in the map. That's an easy thing to do. The other way to do it, which I'm tempted to do because it's slightly suspect in terms of, maybe we're going to be talking about code coverage. Maybe we're going to be talking about counting the number of times an individual instruction is executed or something like that. Maybe we want to have along with the instruction stored, a counter that keeps track of how many times that instruction has been visited. And for this part of the program, we're just going to stop as soon as that counter gets incremented to 2. But if it, later on, those rules might change. So I think I'm going to do it that way rather than keeping a separate list or a separate map. So let's start defining. Okay. Get your puzzle input. Okay. There's a fair amount of it here. Copy that. And then go to input.txt. And paste it in. 638 instructions. And the last instruction is jump +1, which is, I presume we're never going to hit that, because if we do, we're going to run right off the end of the list, and it's going to be bad. So that's the kind of thing that we have to watch out for in our opcodes. So the first thing we need to do is to create our data structures, and then we can write a parser to read this stuff into our opcodes. So I am going to start with actually just creating a separate VM as a vm.go, because I feel pretty confident we're going to reuse this based on several years of having played with these puzzles. So we're going to do package main, and we're going to start with a data structure. So we have to have a type, and one of our types is instruction. And the instruction is a struct. Struct. And it's going to have a opcode, which is string, and it's going to have an operand, which is an int, and it's going to have a run count, which is also an int. And then I am going to, we're going to end up implementing a bunch of functions that will maybe a big case statement that will execute instructions. But first we need a VM, and then we can figure out how to handle that. So let's do a type VM, which is also a struct, and a VM needs an instruction pointer. Now, this is a case where if you write assembly, IP is your instruction pointer. It's the index within your chunk of memory that is the address of the next instruction that will be executed. So IP is such a common term for that, that for me that's the natural thing. You maybe want to use a longer word for people who haven't done this. I don't know. I'm just going to call it IP. And it's an integer because our memory is going to be just an array of instructions. So our instruction pointer's that. We have an accumulator, which is an int, and we have a memory, which is a slice of instructions. I'm just going to leave it like that for right now. So we are going to need VM is going to need a function to it's going to need a function to I know Go typically uses just a single value for this. I like calling it VM though rather than V. It just feels better to me, so I'm going to call it VM. And it's going to need a load method, and it's going to take a let's give it a file name. File name is a string, and it's going to return an error if it cannot load, otherwise nil. So we're going to load, and we are going to, so our typical main.go, which does this, I can actually move this into the VM's load routine. Whoops. So save this and let the editor do its thing. So we're opening the file, and instead of saying open of input.txt, we're going to open a file name. Now we want a nil VM, the zero value of a VM to be a valid VM. So later on, if we try to run it on a new VM that isn't initialized, then run will have to check whether memory is nil. But in this case, we're going to open the file name, and instead of log that fatal error, we're simply going to return error. And do the same for down here. So we're opening the file. That gives us a file object. Then we read all on the file object and get a slice of bytes. And then we do strings.split, converting that slice of bytes to an array of strings on new line. And we have all the lines now are as an array of strings. And now we are going to initialize, we're going to convert all of those to instructions by parsing them. So for line in range of lines, we're going to range of lines. So instruction is a instruction initialized with oh no, sorry. Let's just do this. And then let's write a parse instruction. Helper function. So we can take a string and we are going to match it. I don't even need to match it, it's just a split. So if we want to work on the wild side here, we could literally do let's do this right. Because we're going to end up reusing this thing probably, so parse instruction is going to return an instruction error, and it's going to so it gets a string, splits is strings.split of s space and then operand is operand error is I think, now this is interesting, I believe that plus is valid, but we'll soon find out. So it's strconv.a_y of splits of 1. So the second half. If error... Oh, actually, I have to return... I don't even need to test for that error. I will just return whatever comes back from error. So now I'm going to return instruction, which is going to be constructed as opcode gets splits of 0, operand gets operand. Run count is going to automatically be initialized to 0 because that's the 0 value of an int. And then we're going to return that instruction, and then we are also going to return ARR, which in this case we hope will be nil. But if it isn't nil, then you'll get an instruction and an error. The instruction will be meaningless. So now we say if ins comma error if we don't have an error, oh no, let's just say if we do have an error, yeah, just do it this way. I don't. So that if we have an error, return error, and otherwise we can use instruction and we can say memory actually, right at the beginning of this routine, we should just zero out the memory we already have. We're not going to load into existing memory. So we can say vm.memory gets a new gets an empty slice of instruction. And now we can say vm.memory gets vm.memory.append, no, wrong language, gets append of vm.memory with this new instruction that we just added. And so great. Well, now we've read all these instructions into memory. We have all the parameters as integers. The run counts are 0. Now, again, just to be sure, in case you get called this on an existing VM, now vm.ip is going to be initialized to 0. vm.accumulator is going to be initialized to 0. And why is this? Expected identifier. Oh, colon equals. Sorry, that was my bad. Just equals. You know what? I'm going to move this up to the top since we need to do all that anyway. right, if error is not equal to nil. There we are. Okay. And then now, if that all succeeded, we return nil. All right. So now I believe we will have loaded and parsed that VM, but let's check and make sure that that actually works. So, oh. So, creating a new VM, that gives us a pointer to a VM, which is what we need in order to load it. VM.load, and the file name we're going to pass it is input sample.txt, and we want it to look in the current directory. So let's try this. Well, that was short and easy. All right, let's try compiling this and see if it works. I don't see any errors. Whoops, I see some warnings though. Oh, because I didn't put comments in. Let's add our comments right now before I test this. By the way, I could have made load be a constructor, and so it builds and returns a new VM would be another way to do that. But it depends on whether you think you have VMs, or you're going to reuse VMs and that kind of thing. In this case, it seemed easiest to just have a VM, have a zero value of a VM actually be a the zero value of the VM be a useful item in itself. That's kind of a principle of Go. Try to make the zero value useful. I don't know. Take your word for it. And take my word for it. Here we go. So we're going to try running this now. So I'm going to do go run main.go as well as vm.go, because when you do go run, you have to name all of the files included. If you're going to build, then you build separately and you name all those files, and then when you run it, you just run the build, you run the executable. But anyway, it loaded and ran without error. Now, actually, that's interesting because I didn't actually evaluate the error in the main function. Duh. No, it's not format, it's log.fatal. Fatal. All right, let's try it again and make sure that we didn't get any errors. Yeah, okay, good. Now, great, we are jamming. Oh, got a new follower. Hey, I don't know how to pronounce ISIS88 or whatever it is, but it's nice to see you again. And welcome. Feel free to chat if you want to too. I will try to notice from time to time that somebody has said something and ask questions, make comments, whatever. I've had some helpful comments. Nice. And the I. I got it. Okay, thanks. Okay, where am I now? So we just loaded the demo file. Now we're going to try to actually interpret it. So I'm going back to the VM, and we need to write a interpreter for the VM. And the question is here, so we're going to take a func, and we're going to do VM star VM run. And right now it's not going to take any parameters, but it might return an error. We may decide to change the parameter thing later, especially if we ever end up having to do something like debugging. But the question is, do you run... Well, we definitely run the VM, but do we want the switch statement of running the VM? Do we want the knowledge of how opcodes work to be embedded in the opcodes themselves? So like an opcode knows what to do and it gets given a VM to do it on. Or do we want the VM to have a switch statement where it just, you know, the opcode's just a dumb object? So I think I am going to take a look at doing... So in other words, the code is either you know, look up the instruction dot execute, and then what you get back, and you pass it a pointer to the VM, and then it modifies the VM. Or we have the VM itself do a switch statement on the opcode, and it just treats the instruction as a data structure. I think I'm going to like it better with the latter, so that the VM itself has the switch statement. Instructions, I mean, they don't exist in a vacuum, and as the VM gets more complex, the instruction, I mean, the two end up being very intertwined anyway, because the instruction has to manipulate registers or whatever it might want to do. So I think we're just going to have the VM, it's essentially a CPU, and so we are going to have a switch statement that iterates. The way this is going to work is we're going to have a forever loop. That may break out at some... It will break out when there's an error, or it will break out when the program terminates. We don't have a statement for what termination means right now. Now we're just looking for errors. Instruction is... Instruction is the... takes the memory, vm.memory of vm.ip. So we take a look at what we... So this is the instruction is that we're about to execute, is what is the value of the IP and what is memory there. Now we are not going to increment the IP here. We're going to increment the IP in the switch statement, because many instructions end up changing the IP, and yeah. I think because of the way the jump statement is defined, I'm not going to implement it here. I'm gonna just leave it and then increment it. And then, so we have an instruction, and Now we're about to execute this instruction, so first we're going to increment its run count. So I'm going to say instruction. Oh. Alright, so this index operation here, I actually have to implement the run count in the VM's memory. I don't want to grab the instruction, make a copy of it, and then increment its run count, because then it won't be modifying the memory. So we actually have to modify the VM's memory. So maybe I won't create this instruction object at all. So we're going to increment its dot run count. And for part A, right now this may end up in a conditional. We may end up passing a parameter to run. But at the moment, for part A, if you ever execute an instruction twice, it's an error, and so we're just going to return that. So we're going to go if VM memory run count is greater than 1 now, we are going to return I want a new error type, and honestly I just don't remember how. I want errors specific to the VM. Errors.new, right? I want it in more recent versions of Go, so errors before Go 1.13. Go 1.13. Oh, cool. Errors. So whether to wrap. When adding context to an area, therefore the new error should wrap the original. So I'm going to say, yeah, this is what I want here. Something that looks like this. Copy. We're going to do our VM is going to have some errors that it uses internally. So then I'm going to say return error infinite loop. There. Okay, that's better. Save this. There it is. Okay. All right. So actually, one of the things I should do even before I try to do this, I have tried to index vm.memory, and I might be outside of vm.memory. If the IP is pointing to someplace meaningless, then I need to fail here and fail without crashing. So if vm.ip is greater than, no, is less than 0, or vm.ip is greater than length of vm.memory, greater than or equal to, right? Then we want to return error and then we're going to define bad memory index up here. Oh. I think rename symbol. There. All right. So now we won't run off of memory without detecting it. We're going to check our run count, make sure that we had an infinite loop. And if we do that, then we'll be able to inspect the VM, because the thing we're supposed to do is report the value in memory at the point that error occurred. So this is good. All right, now we're going to switch on the opcode. Dot opcode. And that is going to be a case statement of all of the instructions that we have to worry about. So far, our instructions are just, let's go back to the problem definition. Ack, nop, ack, jump, and nop. So, case ack, case jump, case op, default. So accumulator gets added the VM dot memory of VM dot IP dot operand, and VM dot IP gets incremented. My dog is upset about something outside, so if you hear a little bit of huffing and puffing and howling, that's him. Shiner. That's enough. It's probably the neighbor. There we go. Thank you. Good boy. Alright. The knob opcode doesn't do anything to the accumulator. It just adds one to the IP. Great. He is a good doggo. He's poor good doggo is suffering from an infection that he can't attack right now, so he's wearing a big collar that keeps him from licking himself, and is feeling sorry for himself for it. But so it goes. Alright, and jump is going to set VM.ip plus equals VM.memory of VM.ip dot operand. And default, if we somehow manage to retrieve a value that isn't one of those, because there's garbage in our input file, then we're going to return an error. Whoop. Well, I guess proper Go styling is lowercase on these things. Sorry. I made a magic key to do this for me, and now I've forgotten what it was. I think it's this. Yes, okay. So, error, bad instruction. And that code is unreachable, which is true. It's an infinite loop, and there's no breaks. So I'm going to just comment this out, because we'll probably bring it back later. This oh, first of all, save it. There we go. So let's just, oh jeez, sorry. Okay, so we have a run, and part A should, so we should be able to call this now. We should be able to say error equals vm.run if error dot back to this for a minute. How did they test? They had errors.is. That's what it is. Okay. Errors.is. I didn't put the VM in a separate package, so I'm just going to say error infinite loop. I'm going to give it that. Let's try that. All right. You know what? This is a virtual machine. And it would probably end up being in its own package someday. Hey. Thanks for following. Nice to see you. Yeah, glad you came by. You can watch the rest of the stream later. I'm leaving them up for playback. So, take care. Yeah, I'm gonna give VM. Oh, Drew. Really nice to see you, Drew. Cool. I had suspicions it was somebody else, so thanks for clarifying. Okay, so where am I going? Oh yeah, I was going to add to the VM. I was going to add an accumulator to retrieve the value of the accumulator. So func. This one we don't need a pointer. Although actually I'm just going to always do a pointer because all of these things it's more consistent that way. So this is just an accessor for the accumulator value, which is a private member of the VM struct. So that later on, if we move this thing into a separate struct, you know, we can get the accumulator out of it. And actually, I think I'm going to change my mind and actually make that be passed by value rather than reference. So this is now accumulator that. And on our sample data, it was valid 5, and I always forget this stupid new line. All right, so that worked, and now I feel reasonably confident that we can do it on input.txt. So let's try it with that. Value of accumulator was 1521. Now actually, I mean, if we wanted to, we could do a quick, I'm just going to do a thing and see how many, let's also count as part of the VM, instruction count is an integer, and so now when we run, we increment the run count, but we're also going to do VM dot insert count plus plus. So we're going to increment that. And so then we're going to get so we can save that. Oh, and I also have to zero instruction count when we load the VM. All right. And now let's try it now. 206 instructions, and let's just go back and do input sample one more time to see that we get the same iterate instructions was 5. Perfect. That's exactly what we wanted. Because if you notice when they did their walkthrough, they said this is 8 exclamation point. So we executed it properly. I'm pretty confident that 1521 is the value we want. So we're going to put 1521 in here and submit it. And that is the right answer. Yay! Okay, part 2. Now, we believe that one instruction is corrupted. Somewhere in the program, either a jump is supposed to be a NOP or a NOP is supposed to be a jump. No instructions were harmed. This program is supposed to terminate by attempting to execute an instruction immediately after the last instruction of the file. By changing one jump or no op, you can repair the boot code and make it terminate correctly. Program terminates by falling off the end. All right, so they're defining falling off the end as not an error. So we need to modify the VM so that that is not that is a normal termination. So my test here that says VM's instead of returning IP out of bounds, so less than 0 will still be an IP out of bounds, but greater than max So if it gets to this instruction here at the end, that means it's a proper termination. So we should expect that to fail. Expect that to succeed. All right, so anyway, I'm going back here and I'm going to say that so we're going to remove this OR and move this into a separate conditional. So actually, here we go. If that curly brace return nil, that is a normal termination. Else I don't need it. I don't need it to say else. There we go. I'll put a comment here that that's what that means. So it's no error if we fall off the end of memory. So now we can go back to main.go. But if error was nil, we are formatting, if error was in fact nil, then we can, oh, I guess this needs to be an else. Wait, what did I do wrong? Normal termination. Why? Oh, I'm missing at least one. No, I'm not. What does this say? Expected statement found right paren. Oh, that's because I thought that was a curly brace. There. Okay, great. Alright, so normal termination here. Now the problem is that we're not... oh. So what I should do is pull all of this out, because we're about to test this. So we're going to have a func run VM of VM star VM. And we're going to build VMs in a loop and run them. So this is going to take VM and run it. It's going to get an error back. If the error is nil, okay, what is this going to return? This is going to return no, that's not what I wanted. I guess I did do part 0 versus part, or part 2 versus part 1. I think so what's going to happen here? I didn't even say this. What's going to happen here is that we need to modify these VMs. We need to go in and start tweaking the individual opcodes to decide until we find one that terminates for us. It's probably maybe amenable to analysis, but we're also probably doing just as well by simply modifying each jumper NOP instruction in turn until we find one that does what we want it to do. Let's do that. But I guess I need to have a part 0 and a part 1. So let's go, or part A and B. A 08A runs the VM and then tells us what's going on. And let's just say, let's just do this and make sure that we still get, do VM. Okay, that still works. Great. Now let's do day B. So we modified our VM, but it still works for us. Day 8B takes a VM, and what it's going to do is it loads it, and then it's going to go and so let's give ourselves the ability to reset the VM. So here we have run, we have load, and what load does so I'm going to take these 3 instructions, we're going to put them here, and we are going to vm.reset. The other thing this has to do though is iterate through memory and reset the counters, the run counts. So for I in range of VM.memory, VM.memory of I dot run count is 0. And I'm going to call this actually after I've loaded all the instructions. Okay, so now we have memory reset. And we are going to what we're going to do is load we're going to go in and toggle It's funny because I would say so what I need to do is go through memory, find the next jump or opcode or NOP opcode and flip it, run the VM, see if it terminates, excuse me, and then if it does, if it doesn't, flip it back. And then move on to the next one. So, I hate this, but, so I don't want to do that as a function at the main level, because VM might end up being like an entire package. So I'm going to do it inside VM, but it feels like a pretty weird little hacky thing to do. I guess I could give the VM give an outside debugger the ability to inspect and modify the VM. You know, that's probably what I really want to do. So let's go func VM opcode at index I returns a string an error if There. That, I like that a little better. So I haven't used I yet. So, otherwise I return bm.memory of I.opcode, comma. Now, instead of returning a string, it's going to be an instruction at, and this is instruction error. Return I'm an idiot. Int. And then this isn't I. This is there. And you know what? I'm going to do this as a reference. Returns a pointer to the instruction at that location so that we can modify it. And then this is no longer, so now instead this can now return nil or return the address of alright, that gives me a nice little mechanism to do 8b. So now I'm going to write a loop, and I'm going to say for I also have to give myself the ability to say how many instructions are in memory, which I didn't do. Wait, I don't want this to be here because it might mess up my IntelliSense. Now I can rename the symbol instruction count to instructions executed. And then I can rename this symbol to be It's a long name, but okay. So now I can just make a size method, and it returns an int, and return vm dot memory dot if vm dot memory is not equal to nil. No, if it is equal to nil, return 0. Return vm.memory length of vm.memory. So that's good. But are there any other places where I should have tested for vm.memory as nil? That one's fine. Reset is fine, because if vm.memory is nil, then this range will be nil and will not happen. Instruction at I think this works fine, because if vm.memory is nil, then I'm going to throw this error. So, size, oops. I could make these into constants. Oh, parentheses. There we go. All right, so defining some opcodes. Oh. Hey, I figured it was you. Yes, I recognize you from Twitter, and of course when we worked together many years ago. So nice to see you, and thanks for coming. And if I missed this and you're already gone, sorry about that. I was heads down. But okay, you don't want to stay for this exciting conclusion. We're almost done. I'm doing this, and now actually, so this opcode is now, instead of being a string, it's going to be an opcode, and this is going to be an opcode. And so we're going to do this, and we're going to do that, we're going to do that. Okay, that's good. Now I can refer to those a little more literal, yeah, in a more literate fashion. And so here we go. We are going to loop, so for I colon equals 0, or range, no, is it a range? No. I is 0, I is less than vm dot size I plus plus, and then save that, and so we have a VM, and what we're going to do is we're going to say if vm dot instruction at, oh no, let's just do this, op air is vm dot instruction at I, if error I don't actually need to worry about this error. I'm not even going to look at that error because I know it's within my range because I go from 0 to size. So if the instruction is either of my two jumper nop, then I need to swap it and run it and then swap it back when I'm done. So op is nop, or op is jump, we're going to just call swap and run. we're done. If swap in 1 returns true, we're done. Oh, yeah. Alright, so let's define our swap and run function. And so now we're going to oh, I don't want to pass VM, I want to pass the app code. Because I don't care, no, I do care about the VM. I have to run. This might be pointless. Let's just do this. Yeah, alright. Alright, sorry, I'm not even talking anymore because I'm thinking. So what I'm trying to do is I'm saying, okay, if the op code is nop, then now we're going to flip it to jump, and we're going to run. We're going to reset the VM, then we're going to run the VM. If the VM's run returns nil, that means that it successfully ran and ran off the end like it was supposed to do, and we have found our result and we're done. So at that point, we need to check the value of the accumulator after the program terminates. So we can do this. And otherwise, well, then we just do op.opcode. Actually, yeah. And then we can break because we're done. If op.opcode, oh, we put the opcode back to we'll do this as switch. Switch op.opcode. case nop, put a jump in there, case jump, put a nop in there, default. If it's neither of those, then we can just continue. But if it is one of those, then we just swapped it. We saved the original. We can reset, run and terminate if we need to run, if we need to terminate, and put the opcode back to its original state. Alright, what have I done? Switch, colon, this isn't supposed to be there. Wait. Oh. None of this stuff is supposed to be there. There we go. Okay. Alright. Swap and run is gone. Save that. So he's given us the same program for input sample. So if we go here, save that, and we run it, after 6 instructions was 8. And that is exactly correct. So we can do this on input to text and get our input and try again. Normal termination after 111 instructions was 1016. I'm gonna see if that works. That is the right answer. We did it. Cool. Yeah. So I'm going to commit this. We're not going to do it in Python. This is something we're going to keep reusing, so doing it in Python doesn't help us. But I'm going to take the rest of the files and commit them all. Solve day 8 in Go with a VM. And push that up to GitHub. So in case anybody's interested, you can look at what's happening. You can see all this code on GitHub. You can play with it. You can make your own modifications. Feel free to use it. It's all licensed as do whatever you want with it code. Yeah. So to summarize, today we had what I think is probably going to be the first of several puzzle problems that include a virtual machine. They don't always happen day after day after day. We may not see it tomorrow, but we'll probably see it again before the end of this thing, where the VM gets more sophisticated. There get to be more code on it. Actually, since we're on a plane with a kid's toy, we'll probably end up, the fiction on the plane will be that while we're on this flight, we're doing a bunch of stuff. So hope it's a long flight. There's going to be some interesting things. We're going to add more instructions, most likely, to the virtual machine. There'll be various tricks and things played. But hopefully you saw something. One of the things about VMs is I've actually written several in my career as things that you have to do for one reason or another. And you can write programming languages that support them. You can write, a bytecode virtual machine is actually a useful thing. Java is in fact running in a bytecode VM. That's how it gets to be the write once, run anywhere sort of option. In past lives, I've implemented a Java-like VM. I've implemented a VM that was intended to be on a cryptocurrency system, and a bunch of others for different reasons. So anyway, hopefully you found some interesting techniques or things that were kind of fun to learn about while I did this, and that will conclude the stream for today. I hope it was fun for you. It was always fun for me to do this kind of stuff, and I'll be back tomorrow with part 9. So have a good night, everybody, and I will see you on the bit stream, so to speak. Thanks.